There's no general method for determining whether an arbitrary transformation is one-to-one or onto, but linear transformations can be dealt with in terms of matrices. So, for example, here's a linear transformation. x1, x2 goes to 3x1 plus x2, 5x1 plus 7, x2, x1 plus 3, x2. Verifying that this is linear is a little tedious, but basically routine. Let's just take my word on it. And let's ask if it's one-to-one and or onto. Well, we're going to deal with this using matrices. We've seen that every linear transformation can be thought of as matrix multiplication. And in the last video, we saw an example where we had linear transformation written in terms of matrix multiplication, and we solved this very problem. So we're going from R2 to R3. It's the E1 and E2 in R2 that we need to look at. T applied to 0, 1 is 3, 5, 1. Sorry, I think I said 0, 1. T applied to 1, 0 is 3, 5, 1. T applied to 0, 1 is 1, 7, 3. Put these together. First column is 3, 5, 1. Second column is 1, 7, 3. So this transformation can be thought of as matrix multiplication. And the question of whether this is onto, therefore also resolves into a question of matrix multiplication. Does this matrix times X equals B always have a solution? Well, let's find out. To find such a solution to this, you'd perform Gauss-Jordan elimination on the augmented matrix 3, 1, B1, 5, 7, B2, 1, 3, B3. Except you're really only performing the elimination on this submatrix. This B1, B2, B3 will turn into whatever. B1 hat, B2 hat, B3 hat. Now, a slight irritant is going to occur. Your very expensive calculator is not going to perform Gauss-Jordan elimination on this matrix for you. I have literally no idea why. Or to qualify that a bit, I know why. It's because you have more rows than columns. But you can perform Gauss-Jordan elimination on a matrix with more rows than columns. You can perform Gauss-Jordan elimination on literally any matrix. So why your calculator should have this restriction, I don't understand. But I'm going to start by swapping rows. It's nice to have a 1 up here, and I can get that with a row swap. Now I'll use this first row to get rid of the second row, multiply by -5 and add. Let's see, -15 plus 7, -8. And I'll use this first row to get rid of this third row, multiply the first row by -3 and add 0, -8. When I now use this element in the second row to get rid of everything below it, we just get 0, 0. This is really good enough for our purposes, but if we wanted to keep going, to be in a Gauss reduced row echelon form, we'll divide this second row by -8. And then we'll use this 1 to get rid of this 3. Boom. I can do what a $100 calculator apparently cannot. And this is enough to answer both our questions. Is it on to? No. because of this row here, 0, 0, if this b sub 3 tilde is anything other than 0, we're not going to have a solution. So this matrix equation does not always have solutions, meaning this isn't onto. On the other hand, if we do have solutions, if this b sub 3 hat does turn out to be 0, well, then x sub 1 is b sub 1 hat, x sub 2 is b sub 2 hat. That's the only solution we have, so the solutions we do have are unique. That is to say, this is 1-to-1. As we've seen, it is not onto.